Right, so today I'm going to do something a little bit different. I'm going to be going through some Oxbridge interview questions for the kind of STEM subjects, so science, technology, engineering, mathematics. So these are the type of questions that I expect a physics, engineering, mathematics student to be able to answer in an Oxbridge interview. Okay, so I did my undergraduate and master's at Oxford, so I helped with the applications process while I was studying at Oxford, and I went through it myself. So these are some of the types of questions that I've heard of over the years, and there is a sort of common theme to all of the Oxbridge sort of STEM application technical questions. Okay, so these are the technical questions. So the first type of questions that I want to kind of answer in this series is, how do you draw graphs? How do you draw a graph if they ask you to draw a certain relationship between two things? Okay, so a typical one is just that they will give you the equation for a curve, and they'd like you to just sort of draw it, think about what it does when it tends to infinity, think about it what it does as something like x tends to 0, find those points that it crosses the axes, and find maybe stationary points or points of inflection, things like that. Okay, so I'm going to sort of teach this kind of thinking process just by giving you example questions and telling you how I might go about them if I was given them in an interview. So here's the first one that I usually give students in our sort of first tutorial if I'm preparing them for Oxford physics, engineering, mathematics, anything like that. Cambridge is the same. Okay, so let's try y equals sine x over x. So this is a tricky function to draw. It actually gets the name sinc x in physics, okay, because we use it quite often. And in fact, sinc squared x, which I might get you to draw in a minute, or I'm going to draw myself, but I'll get you to think about it in a minute, is used even more often, and maybe might have even been seen at A level if you do A level physics. So let's think about how we might draw this function. So I'm going to draw some axes down here first. And there we are. So that's a y-axis and an x-axis. What I might typically think about straight away is where this will cut the x-axis. Okay, in a question like this, I might lead the students thinking by first saying, think about what happens as x tends to 0. So as x tends to 0, what happens? So that would be a kind of hint for this question. I would usually guide a student in with a little bit of a hint. So I didn't say what happens when x is 0. I said what happens when x tends to 0. So thinking about this equation, you should know that sine x looks... Okay, I'll draw it on here in a different color. Draw it on in red, maybe. Should know that sine x looks like this. Okay, and we're talking about radians here. Usually you'll get this question in radians. So, okay, and it kind of repeats like this. Okay, not the best drawing in the world, but this is up at 1 here. This is down at -1 here. And it crosses at pi and 2 pi, and it would again cross here at 3 pi, etc. And also at -pi and 2 pi, -2 pi, -3 pi, etc. Okay, and this is 0, 0 here. Okay, so that's a drawing of sine x. So if we think about what happens when sine x equals 0, it's in fact equal to 0, but so is x. And you get a mathematical error, or it's not allowed in mathematics to divide 0 by 0. Okay, it's an undefined function at 0 then. That's what you can conclude, is undefined at 0. But you might be asked to think about what happens in the limit as x approaches 0. Okay, as x approaches 0. So how does sine x over x behave as x approaches 0? And there are a number of ways that candidates might approach a question like this. So probably the most typical way for a sort of British student to approach this problem would be that if they're studying A-level maths, then they may have heard of the small angle approximation. Okay, the small angle approximation. And these small angle approximations, they actually stem from something else called the Maclaurin series. So we'll talk about those in a second. But the small angle approximation says that as x or theta, whatever your variable is inside your sine function, as sine x is approximately equal to x when x is small. Okay, so some students will tell me, oh, that's only for x is less than 10 degrees, or this is only for x is less than 5 degrees. It depends on the accuracy that you want when you say that sine x is approximately equal to x. So at no point is it really true that sine x is equal to x apart from at 0. Okay, then that is true. They are equal to each other at 0. This small angle approximation, yeah, that's a good sort of good way to think about it. You know, is it true for less than 10 degrees? Is it true for less than 5 degrees? No, you know, neither of those are really true. It just depends on the error that you want. So if you said you want a 1% error, there'll be a certain angle for which you need to be below that to get that 1% error. If your error was instead going to be, I don't know, 0.5, then you'd need an even smaller theta for that. Okay, so that's the small angle approximation for sine x. And just in case you want to know, the small angle approximation for cos x, well, if it's very small, you can approximate it to 1. But if you want to include x in as a variable, you might want to consider something like 1 minus x squared over 2. Okay, and for tan x, well, you can just think of this as sine x over cos x. Usually people approximate this also to x. So x over 1 minus x squared over 2, well, the 1 on the bottom will dominate, especially as x is small. X squared is going to be incredibly small. So this is kind of optional. I guess you want to see on a case-by-case basis whether you want to include this x squared here. So if you have some sort of relationship between cos x and y or something like that, then you don't want to just say, well, when x is small, y is 1. You might want to say when x is small, y goes as 1 minus x squared over 2. And that's just an approximation, but it's a better approximation than just saying 1. Y is always 1 when x is small. Okay, so that's just a sort of example of when you might use these. Other students may have heard of the Maclaurin or Taylor series. So there are in fact series expansions for these functions here, and they're a polynomial series. So you can actually say that sine x is equal to this infinite series that goes x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. And it carries on like that. So it's alternating positive and negative, and it's only the only the odd powers and the odd factorials on the bottom. So you could, of course, call this one 1 over 1 factorial there, if you want to be precise, I suppose. Okay, so that's the pattern for sine, and there's a reason why it's only the odd valued powers and factorials on the bottom, and that's because the function of sine x is actually an odd function. What we mean by that is that it has a symmetry about it. In fact, if you rotate sine about the origin by 180 degrees, then it's invariant under that transformation. So if you rotate it about the origin by 180 degrees, you'd actually find that sine maps perfectly onto itself. Okay, so it doesn't really change. Another way of saying this is that odd functions, if you have a function that's odd, Okay. So let's say f of x is an odd function. If I perform that transformation where I say I'm going to replace every x with a minus x, you would in fact get minus f of x, which means that if you reflect, so if you take an x here, then f of minus x, so minus x is here, is actually the negative of f of x. So this is f of minus x, okay, and this is f of x here. So you can see that that's true for the case of sine. So sine of x is equal to the negative of sine of minus x. Okay, so sine is an odd function. And so are all of these. So x cubed is an odd function, x to the 5 is an odd function, x to the power of 1 is just an odd function as well. So you can see that that's true if you think about x cubed. If you perform this transformation and you instead look at minus x cubed, you in fact get minus x cubed. Okay, so the minus times a minus times a minus is going to give you a negative sign here, and that suits this kind of this transformation. If you put a minus sign in front of every x, then you're going to get a minus sign at the front. That means it's odd. Okay, and that will be true for any odd-powered any polynomial with odd powers. That would be true. Okay, if we do the same thing for cos or cosine, you in fact get 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial plus, minus x to the 6 over 6 factorial. And then dot, dot, dot. So these two are the Maclaurin series expansions for sine and cosine. I'm not going to bother with the one for tan here. There is one for tan. You can look that up if you want it. But you can see this is just the opposite of the sine. This is all of the even powers. Okay, all of the even powers, and still alternating between positive and negative. So you can think of this 1 as x to the 0 over 0 factorial, if you like. You define 0 factorial as 1. So you can think of it like that if you want to think of this as a series and think about the next term and the term after that. And in fact, cosine is what we call an even function. So if I were to draw cosine on this graph here, I'll take a different color to do it. You can see that, okay, I'm just going to draw part of the cosine curve. We don't actually need it for this question. You can see that cosine actually has symmetry about the mirror line of the y-axis, or x equals 0. So in fact, for even functions, you have f of x, or f of minus x, is equal to f of x. So this means that if you perform that reflection in the y-axis, then you completely map onto yourself. Okay, so it doesn't really matter if you put a minus x into an x into cosine or a minus x, you will get the same f of x value. It doesn't matter. Okay, so that's just what an even and an odd function are. And why did I tell you all of this about the Maclaurin series? So Maclaurin. So this is the Maclaurin series for each of these. Okay, so these are Maclaurin series. Why did I tell you this? Because this is where the small angle approximation comes from. You can see that if you're using a very small x, then x is much smaller than x cubed. Say you put in 0.001, then 0.001, that's 10 to the minus 3, right? 10 to the minus 3 cubed is 10 to the minus 9, and then you're dividing that by 3, so it's even smaller. So you can think, if you're actually using a very small x, all of this will be shrinkingly small compared to just x. Okay, so that's why you can say for very small values of x that sine x is approximately equal to x. If you do the same thing with cosine, you can either cut it off here and say, well, all of this is very, very small, so I don't care about it, and I'm just saying cos x is equal to 1 or approximately equal to 1. Or I could actually say, well, no, I want to keep an x in there so I can kind of say how cos x is going to vary with very small x, and I can say it's kind of quadratic. So if you actually know what your expression you're trying to get towards is going to be, and you know it's got some sort of quadratic in it or a square root, you might want to include that second term, x squared over 2 factorial. But for other questions, you may want to go to further along these Maclaurin series to get a more accurate expression for what sine and cos x are. But most of the time, you're not gonna need to do that. Okay, so that's where these small angle approximations come from. So going back to this question, what actually does happen in the limit of when x tends to 0? And I'm looking at sine x over x. Well, I can say that sine x is approximately equal to x for small values, but as it tends to 0, I can say effectively that is x. So I get x over x, which is just 1. So this limit tends to 1. If you have studied around your subject, read around mathematics, then you may have heard of Loptails Rule. Okay, Loptails Rule. I'm going to write that down. Loptails Rule. And this is a rule for evaluating tough limits. Okay, limits that you can't evaluate. Things like sine x over x. It's actually not. You can't evaluate sine of 0 over 0, but we can evaluate this limit. And one of the ways you can do it is Loptails Rule says really if the limit of of x approaches some value, let's call it c of f of x over g of x, well, that will also be the limit as x approaches c of the differential of x over the differential of g. Okay, so I'm not using the quotient rule here. I'm just saying the differential of the thing on top and the differential of the thing on the bottom. Okay, so if you did that in this case, and you should really only use this if you can't think about. So a lot of functions you could just put in c here and find the solution. If that is just undefined at c, if f of x over g of x is undefined at c, then you want to be using Loptails Rule. So you don't have to use Loptails Rule for this question. See, we found the answer just by thinking about the Maclaurin series and the small angle approximation, but you could use Loptails Rule. So how would that work in this case? Well, in our case, we've got f of x is actually sine x, and g of x is actually x. So if we want to find the limit as this approaches, in our case, 0, we differentiate both of those functions. So differentiating sine x, I get cos x, and differentiating x, I just get 1. And if I evaluate this at x is 0 now, I can see that cos x is actually 1 at 0. Sorry. Yes, it's 1 at 0, 1 when x equals 0, so I get 1 over 1, which is 1. So it does work. And it gives the same limit as we see here for sine x over x when we use the small angle approximation. Okay, so this is just, this is one of many ways that you could do this problem. So I've actually kind of shown you sort of 3 ways here. In your interview, you just have to say 1. You can say small angle approximation, sine x approximates to just x, so this would be x over x, which we can say is 1 when x is shrinkingly small. Okay, so if I draw these axes again, I'll draw them down here this time. So let's say that's my y-axis, this is my x-axis. Okay, I'm looking for the limit as x approaches 0, and I actually know what that limit is. It's actually 1. We've evaluated that now. So I'll put a small ring around y equals 1. Actually, I'll make it a bit higher because then I'll have a bit more space for this question. And I put a ring around it because you can't actually evaluate the function at 1, but I know it approaches that, and it approaches that from both sides. So you can say something along these lines. Okay, so up here, I actually drew, in red, I drew sine x. So it might be interesting to draw the other part of this function, the 1 over x, and think about what happens when we multiply them together. So if I choose another color here, and I draw 1 over x, Okay, it's going to look something like this. Okay, so it's an asymptote approaching 0 there. It can't ever touch the y-axis either. And same sort of thing happens here, apart from it's negative. Okay, so that's my y equals 1 over x graph here. Now actually I'm going to be multiplying together sine x and 1 over x to actually find what this graph of y equals sinc x or y equals sine x over x looks like. But as I said, you might want to consider the points where this is going to be equal to 0, and one of them is going to be at pi. You can see that because sine of x is 0 at x equals pi, and x on the bottom is just going to be equal to pi. So we've got 0 over pi, which we can evaluate to 0. And actually that's true for any whole number integer value of pi. So we could mark that on our diagram. We could say, here's pi, here's 2 pi, maybe we'd do it up to like 3 pi. Okay, and all of those points are going to be 0. And the same here, pi, 2 pi, and 3 pi. All of these negatives, sorry, there we are. And something that I could say, and this is why I wanted to talk about odd and even functions, is it might be nice to always check if your function is even or odd. So in our case we have sine x over x, and 1 over x is an odd function. You can see that here. If you rotated 1 over x about 0 by 180 degrees, you'd map it onto itself. You can also think about this rule here, that if we put minus x in for x, do we get minus the original function? Yes, we do. If we put a minus x in here, that's the same as saying minus 1 over x. So that's true. So that's an odd function. And we already said that sine is an odd function. So we're actually dividing an odd function by an odd function. And you can think about this, but if you apply this transformation to our sine x over x, so that's like saying put a minus sign in here, put a minus sign in here. Well, I've already explained to you that sine of minus x is actually minus sine x. So get rid of that minus sign on the inside. You can move it to the outside. And now we have a minus over a minus, so those would cancel. So in fact, if you do make this transformation, you put a minus x in for every x in the function of sinc x, it actually obeys the even function rule. Okay, so sine x over x is actually an even function. And I think you can show that if you have an odd function divided by an odd function, you will get an even function. Okay, I think that's possible to show that. Okay, so we know that actually if we draw it for one side, then because it's an even function, because it has this symmetry about the mirror line of the y-axis, it will look exactly the same on the other side. We also know it passes through these points pi, 2 pi, and 3 pi. We could sort of evaluate what it's going to be at pi over 2. At pi over 2, sine is 1, and so we have 1 over pi over 2, so it's going to be 2 over pi. 2 over pi is about 2/3, let's put it there, 2 over pi. Okay, so that would be a point. And we could do the same thing for 3 pi over 2. Okay, at 3 pi over 2, sine is negative 1. So we would get negative 1 over 3 pi over 2, which is going to be negative 2 over 3 pi. 2 over 3 pi, negative 2 over 3 pi is approximately negative 2 over 9. Okay, so I'm going to put that there, but maybe it'd be a bit smaller. And I could do the same thing for 5 pi over 2. 5 pi over 2 is actually going to be at 2 over 5 pi, so maybe 2 over 15, really. 2 over 5 pi, around 2 over 15. So that point will be there. Okay, and if I join up all of these dots now, join up all of these places that I know the line should go through, then I can say what this curve is going to look like. And I've already said that it's an even function, so it's going to be exactly the same on the other side. So let's take it through 2 over pi. Let's take it through the axis at pi goes down to 3 pi over 2, then back up. and then it's going to do something like this. And we know that actually each trough and peak following this, they're going to get smaller and smaller. In fact, you can draw, it's not quite an envelope function, and I'll explain why it's not quite an envelope function in a minute. But because sine is always 1 or -1 at all the half values of pi, you can kind of draw this envelope function that would be 1 over x. So 1 over x has to sort of come down here. It would pass through this point here, and then this point here would also be on 1 over x, and so would the next one, and the next one, and the next one. Okay, and the same for -1 over x. It would pass down here, and that point would be on the -1 over x curve, this point here, and so would the next trough down here. Okay, so if I continue this curve in green, we know roughly what it's going to look like on the other side because it's just a reflection. It's going to have this same kind of, it's going to have a symmetry. Okay, and each of these peaks and troughs is going to decrease in height, okay, each time. Okay, so that's what y equals sinc x should look like. And I think I've argued well where the 0 points are going to be. If we talked about when x tends to infinity or negative infinity, well, 1 over x tends to 0, and its sine multiplied by that. So sine is a bound function between 1 and -1. So as this tends to infinity, our graph is going to tend to 0. Okay, our sinc x is going to tend to 0 at both of those points. So we've talked about all of the interesting points here. I'm going to pause the video here, and maybe in the next video we can talk about the exact location of these peaks and troughs. Are they in fact on 3 pi over 2 and 5 pi over 2? So that's typically something that'll ask next, just to see if a student can argue well about where these maxima and minima are going to be. Okay, thank you.